All right, so now that we talked about the first law, let's start talking about the second law. So one thing that the first law implies as well that I didn't write down last time is that what for us to have a change of motion, we have to have a force. Well, remember from kinematics that for us to have a change in velocity, remember velocity is equal to the initial velocity plus the acceleration times the change in time. For us to have a change in velocity, we also have to have an acceleration. And again, what Newton's law says is that what a change in velocity implies that we have a force, but simultaneously, this tells me that a change in velocity means that I have to have an acceleration. So basically, what the first law also implies to me is that using these two things simultaneously, that's what the force that must be directly proportional to the acceleration. So what this tells me then is that what force and acceleration are effectively the same thing. So in this case, for me to have a change in velocity, I have to have an acceleration, but to have a change in velocity, I also have to have a force. So therefore, force must be directly proportional to an acceleration. So the next question is, well, how are these guys actually related to each other? Well, we can again use another video to try to figure that out. So in this video, what I'm going to do is I'm going to hang a bucket on one side and a 2.5 pound weight on the other side. And I'm going to have that over a string, over a pulley. This is actually what's called an Atwood machine. We'll talk more about this as an example. But basically, in the first case, I'm going to have nothing in the bucket. And I'm going to drop the mass, and we're going to see how fast that the bucket accelerates upward. Then I'm going to pull the bucket back down, and then I'm going to put a can of beans in here actually, just to give it a little more mass to it. And now this time again, I'm going to do the same thing. I'm going to drop the 2.5 pound weights, and let's watch what happens to the acceleration of the bucket. Again, how fast does the bucket move up? So let's watch the video. Great. So now that we've seen the video, what can we say? So in this case, we can say that's what? Well, in the second case, where I had more mass in the bucket, how did the acceleration or the change in velocity of the bucket in the second case compare to it did in the first case? Well, if we watch it again, what we can see is that what? In the second case, when it had more mass to it, it actually moved up slower, which means that the acceleration was less in the second case than it was in the first case. So what that tells me then is that what? The less mass, the more acceleration, and then the more mass, the less acceleration, right? And in both cases, I had a fixed amount of force because I had that 2.5 pound weight, which gave me a fixed amount of force. So in this case, what I can say then is, well, what? My acceleration then is if the mass goes up, the acceleration goes down, and if the mass goes down, the acceleration goes up, which means these two guys have to be inversely proportional to each other, which tells me then that simultaneously, the magnitude of the acceleration at least has to then be inversely proportional to the mass, right? So if I put these two things together, what this tells me then is that the force divided by the mass then must be equal to the acceleration, which ultimately then tells me that my force then is equal to the mass times the acceleration. Now, in general, though, this is only if I have one forces, but if I have multiple forces which are acting on it, in this case, I can then write down that the sum of the forces, this is the Greek letter sigma, so the capital sigma for sum, is then equal to the mass times the acceleration. So this expression here, this is what we lovingly call Newton's second law. So Newton's second law is actually just an operational definition of how force relates to mass. So this thing says that the sum of the forces, also what's known as the net force, is simply equal to the mass times the acceleration. Now, this is a very simplistic looking expression, but there's a lot buried inside of here. All right. So let's talk about this expression for just a second and see how this thing is actually more complicated than it looks like. So let's start off with the right-hand side. So the right-hand side is actually pretty easy. So the right-hand side is simply a yes or no question. So basically, all I'm going to do is I'm going to look at a situation. I'm going to say, is my system accelerating? Yes or no? If it's accelerating, I'm going to say yes. In that case, I get simply MA. So in this case, this would give me an MA. And if the answer is no, it is not accelerating. It's either moving at constant speed or it's stationary. In that case, I'm going to say no, and then the right-hand side is simply equal to 0. Right? This is also what we call statics. We'll talk more about statics later. So the right-hand side is actually pretty easy. So it's simply a yes or no question on, is this guy accelerating or not? Right? Now, the left-hand side, this is where all the complication comes in. This is the y side. The right-hand side is the how side. Right? How is it accelerating? Is it accelerating or not? The left-hand side is the y. So the left-hand side tells me, why is this thing accelerating or why is it not accelerating? So in this case, if it is accelerating, what it tells me then is I have some sort of net unbalanced force, meaning there's no opposite force to it causing it to actually accelerate. If it doesn't accelerate, what that means then is that all the forces are balanced and this thing will not actually accelerate. So for example, here, again, if I put my water bottle in my hand, this thing is not accelerating. The reason for that is that what? This thing has a mass to it, so it has a weight. I'll talk more about that in a second, which is pulling it downward. And then it also has what's called the normal force from my hand pushing it upward. So all that tells me is my normal force from my hand must be equal to the weight. Okay? Or in this case, if I take the cup and I drop it, was it accelerating? Yes. Why? Well, in this case, again, it has a mass to it, so it has a weight pulling it down, but there's no normal force here, which is causing it to go up, so it has to accelerate downward. Right? So in this case, I have an unbalanced force, where in this case, I have balanced forces. Okay? Now, the left-hand side is actually even more complicated in the fact that it is a complicated geometrical representation of all the forces acting on the object. Now, why is that complicated? Well, it's complicated because as I change the geometry, I change all the forces. So for example, in this case, where I'm holding my water bottle like this, nice and flat, but now if I start to rotate it, I put it up like this, now I've changed all the forces acting on the system, which means that now all the forces will be different and the value of this expression will now be different. So what this means is that there is no such thing as one equation of a force, because as I start to change things and as I start to rotate it, then the forces that are acting on it will also change appropriately. Okay? So that means every time I make a small modification, I have to resolve my system to find a new acceleration, because now all the forces have changed, which now is going to change the acceleration of my system. So it's very complicated in the fact that I have to redo everything every time I make a small geometrical change, or if I even add a force, or if I take a force away. So for example, got something over here. If I take something as simple as my keys here, and I put them down on the table, let me change this a little bit so that these guys are here, right, like this. It's a little blurry. Sorry. There you go. So in this case, if it's just sitting there, I have a different force than if I would if I pulled up on it a little bit. Right? So in this case, is as soon as I introduce other forces, other things in the system change, and then I have to take those things into account. So we'll see how you actually do this in a practical case, but just note this is Newton's second law. So Newton's second law seems very simplistic, simply F equals ma. Can't be that hard, but it actually is more complicated than you would want to give it credit for. So again, the right-hand side is simply a yes or no question, meaning is it accelerating or is it not accelerating? Yes or no, that's nice and easy. The left-hand side is where all the complication comes in, because now I have to look at the geometrical interpretation of what's actually happening in the system, and then use that to then determine the acceleration on the system. So the point of using Newton's second law then is to simply find the acceleration of the system. Now, for us for now, since we're going to have constant accelerations, that means we're going to be able to couple this now with kinematic equations. So now what we're going to do is we're going to use Newton's second law to find the acceleration. And then once we have that acceleration, we can then plug that into our kinematic equations to be able to find whatever it is that we want from there. So for example, how far did it go in 1 second? How fast is it going in 1 second, etc. Or vice versa. We could actually use kinematics to find the accelerations and then use the acceleration then to find some sort of force that we don't know. Right? Oh, good. So let's start talking about then typical forces we're going to encounter. So typical forces. So as we start investigating forces here, these are some typical ones we're going to see. So the first one, it's what's known as the weight, also known as the gravitational force. Now, this is the gravitational force near the surface of the Earth, but again, nonetheless, it is a gravitational force, which for most of this can usually call us the weights. So this guy, we're going to typically either write it as F sub G or as W. Right? Either one is appropriate. We can use each one, but in this case, we're going to say it's the gravitational force or simply the weight. And here we're going to call it little g, just to make sure that we know it's near the surface of the Earth. And this guy is defined as m sub g. Okay. So this is the weight. Now, one thing to pay attention to with the weight, unlike mass, is that weight is dependent on where you are, which means that your weight will change depending on where you go. So for example, if I'm here on the surface of the Earth, I have a particular weight, but then if I go to some place like the moon, which has 1/3 of the gravitational acceleration that we have here on Earth, then if I go there, my weight has decreased by 1/3. Nice. Right? As opposed to your mass is consistent no matter where you are. The mass is simply roughly the amount of volume that you take up, as opposed to your weight, which is that volume times g times the acceleration due to gravity. So if I was free floating in space, for example, I would have no weight to me. The reason for that is there is no acceleration due to gravity, at least if I'm far enough away from certain things. So in that case, I have no weight. I'm completely weightless. But here on the surface of the Earth, I have a particular weight to me. So this is what we call, excuse me, in this case, the weight. Okay? The next one we're going to see a lot is what's known as the normal force. So I've already used this word before, but let's talk about the normal force. The normal force we're going to denote by a lowercase n with a vector sign on it. So what's the normal force? Our normal force is a reactionary force. Reactionary force due to the interaction between two objects, and it's perpendicular to the interface between the objects. All right, so what does that mean? So what that means is, let's say I have a box. So here's my box, and then I put another box on top of that box. Okay, so here's the second box. Okay. So what this means is that what? If I look at the top box, I now know my top box has a gravitational force to it. And since the acceleration due to gravity always points downward, that means that my gravitational force will always point downward. So this is my mg. Now, in this case, because I have two boxes sitting on top of each other, that means there's an interface between the two. So I get a resulting force between the interaction of these two, which basically means that what? The top block must be pushed up by the bottom block because the top block can't fall through the bottom block. So this means that it's a reactionary force, meaning it's a force that says, hey, I'm here, you can't fall through me, that's not fair. So in this case, I get a normal force, which is then perpendicular to the surface, or in this case, my top of my box, and this is what we call the normal force. So a normal force you can think of as what? A force that is there between two objects, not allowing the objects to pass through each other. So again, if I go back to my water bottle in my hand here. So in this case, again, my water bottle has a gravitational force pulling straight down, but it's not falling down, which means the normal force in this case must be pushing upward. In this case, I know it's pushing upward because my surface here is flat, so perpendicular to this way. Now, do this gets a little bit lighter. So same thing here with this case, but now notice if I take the case and I rotate it, so that now it's at a slight angle, it's not flat anymore. The normal force is perpendicular to the surface, which means my normal force is now pointing this way, right? So as I rotate this surface, my normal force is perpendicular always to that surface, which means my normal force now points in different directions as I rotate. Okay? Give you another example. Here's my wall over here. So now if I push against the wall, now the wall is pushing back on me, and what's pushing back on me is the normal force. So in this case, since the wall is flat here, the normal force then is pushing me in this direction or away from the wall, always perpendicular to the surface. So this is the normal force. So normal force then is a reactionary force between two different objects, where one of them can just simply be a table or a track or anything like that. But again, it's a force that's there that says, hey, you can't fall through me because I exist. Right? I'm not made out of air. You can't pass through me. So you have to be pushed back in the other direction. And that direction that it's pushed will always be perpendicular to the surface between the two. So one thing that's kind of complicated about the normal force is that it never has exactly the same equation. It's going to be dependent on actually the net force acting on the system. So let's look at this box here. And let's kind of see how Newton's second law works. So let's say, in this case, I want to know what's the normal force. So in this case, let's see, how do we actually apply? Now, in this case, since I only have two forces which are acting both in the y direction, I'm going to go ahead and look at only the y direction. So in this case, let's say my positive y direction is upward. Now, one thing that's nice about Newton's second law is that since it is a vectorial statement, since I'm working in Cartesian coordinates, I can look at the sum of the forces in the x direction, and I can look at the sum of the forces in the y direction independently. So all that means then is I can look at the sum of the forces in the y direction, and I can look at the sum of the forces in the x direction. Right. Now, again, how does this work? How this works is I can say, well, again, going back to my yes or no expression, I simply say, is this guy accelerating or not? If the answer is yes, I get an MA. If the answer is no, I get a 0. In this case, since it's static, it's stationary, it's not doing anything, it's simply equal to 0. So in both cases, I get 0. Right? So in the x direction, it's not accelerating. In the y direction, it's not accelerating. Now, in the x direction, there are no forces, so I get 0 is equal to 0. So technically, I don't care. I don't care about that expression, but what I do care about here is the forces which are acting in the y direction. So here, the way I would now look at this is I'm going to look at the sum of the forces in the y direction. So I'm literally going to look at what forces are in the y direction. So according to this picture here, which is what's called a free body diagram, my free body diagram then tells me all the forces which are acting on my body, or my body, on my object. So in this case, it is a visual representation of all the forces. So I'm simply going to look at it and I'm going to see what forces do I have in the y direction. Well, in the y direction, I have my normal force and I have my weight. Now, according to my coordinate system, I chose a positive y to point upward. So in this case, my normal force will be positive because it's in the same direction as my positive y, and my weight will be negative because it's in the opposite direction as y. So here I'm just going to say, well, I have my normal force minus my weight is then equal to 0, which means my normal force then is simply equal to my weight. So in this example here, my normal force is simply equal to the weight. Nice. Now what would happen if I tilt it? So let's say now I'm going to put it on an inclined plane. So here's my inclined plane. Here is my box. And again, here I know I have my normal force, which is going to be perpendicular to my surface. I have my gravitational force, which always points straight down. And in this case, again, I want to know what is my normal force. So let's say, what is the normal force on the system? Now, again, since I'm looking for the normal force, I'm going to go ahead and choose that this is my y direction. So that this becomes my angle of theta, and then this becomes then my x direction. Right? Now, typically when I'm working on an inclined plane, I'm going to work with this tilted coordinate system just because it makes my life easier. And I'll kind of explain that to you why now. So let's say this thing did have an acceleration, so it's going to accelerate down the plane, right? So in this case, if I use this tilted coordinate system, notice what's happening here is that what? Because these two are 90 degrees, what that means then is that all the acceleration is in the down direction, which is the horizontal direction according to my coordinate system, which means in the perpendicular direction along the y direction, there is no acceleration. So in this case, what I'm doing is I'm forcing all the acceleration to be in one direction, as opposed to if I took my traditional coordinate system, which is say this one with this one. So this was my x direction. This was my y direction. Notice what happens here in this case then is that my acceleration is actually two-dimensional, which means that there's a component of the acceleration in both the x and the y direction. So I'd have to worry about the components of the acceleration, as opposed to the black one, where all the acceleration is only in one direction. So I don't have to worry about the perpendicular direction because there is no acceleration. So this is why it's much better to use the rotated or the tilted coordinate system. So let's use that one. So in this case, since I want only the normal force, I'm going to work with only the y direction. So I'd say the sum of the forces in the y direction, again, are equal to. So is it accelerating in the y direction? Again, I already answered that. The answer to that is no. So I'm simply going to get a 0. And again, I'm going to look at the forces which are acting in the y direction. So again, in the y direction, I have the normal force. I have all of it here, and it's all pointing in the positive y direction. We get a normal force. And then it's not accelerating because I have this component here of mg. Now again, here I have to be careful. Just because it's in the y direction doesn't mean it's mg sine of theta. So we have to be careful relative to where the angle is. So note that again, this angle here is exactly the same as this angle here. And the reason for that is alternate interior angles of triangles and all that good stuff. I'll let you try to prove that to yourself, but if you can't, go ahead and ask. But basically, since this angle here is adjacent to this guy here, that means this must be the cosine piece. So this is actually going to be mg cosine of theta, is this piece here. Now, since this is pointing in the opposite direction as my positive y, it has to be negative. So I get a minus mg cosine of theta is then equal to 0, which means in this case, my normal force then must be equal to mg cosine of theta. So in this case, as soon as I go from here, where the entire normal force is simply mg, to here, it is now reduced by cosine of the angle. So what that means is that what this normal force is going to keep getting smaller and smaller and smaller and smaller and smaller until eventually I hit 90 degrees, where this thing then is going to go to 0 normal force. At this stage, it'll just go under free fall, so there's no normal force because there's nothing pushing it into the wall like this. It's just simply under free fall. So, so again, a normal force is something that doesn't have an exact equation to it. It's completely situational dependent. All it means is how much contact is there between the two objects. So as I start to tilt it, there's now less contact between the two. Or, for example, if I have my keys sitting here, if I have normal force here, but then as soon as I start pulling up with my string, that's then going to reduce the size then of the normal force acting on the system. So there is no one equation for the normal force. It's going to be completely situational dependent. This goes back to what I was talking about earlier, how the left-hand side of Newton's second law is completely geometrically determined in the fact that it's going to change depending on the geometry of the system. So this is what we call the normal force. Now, let me ask you another question for this. If I was standing on a scale, let's say here I am, and I stood on my scale, what would my scale tell me? Would it tell me my weight? Well, it turns out that no, what the normal force actually reads to me is my normal force. So in this case, what I would happen is what? According to here, I would then have what? My weight falling downward, mg, but then the normal force from the scale would be pushing on me in this direction. So what the scale would ultimately tell me then is what? Well, looking at the scale actually. So the scale would actually then tell me the normal force. So how much force is actually being pushed down then on the scale. So this is what the scale actually tells me. So the scale reads the normal force. How do I know that? Well, I know that because if I was standing, say, on my scale, and then I grab the side of the table here and I pull myself downward, what would then happen to my weight? Well, it would increase, right? Because now my normal force is increasing because I'm adding an extra force downward, even though I haven't gained in weight, but I'm simply pulling myself downward, which is then causing my normal force to go up, making my weight go up. Or, for example, if I pushed myself like this up on the table, right, taking away some of my normal force, in that case, it would say my weight decreased, even though I haven't actually gone on a diet and lost any weight. I'm simply applying an extra force downward, which is decrease the amount of the normal force, causing my weight to go down. Okay? So this is what a scale actually tells me. So a scale actually reads my normal force and does not read my actual weight itself. Okay? So as another example of this, let's look at this case here. So let's say, what would happen to my weight if I was in an elevator? And let's say that elevator was accelerating. So I want to see what happens when the the acceleration of the elevator was upward versus if the acceleration was downward. So let's look at that here. So let's say here is the elevator. Okay, here's the scale. And then here I am standing on this guy. So that's what? I have a gravitational force pulling me down in this direction. So mg. I have my normal force from the scale pushing in this direction. So this is my normal force. And then I'm going to have some sort of acceleration. So in one case, I want it to accelerate upward. And then in the other case, I want it to accelerate downward. Okay. We want to see what's the difference between the two. So let's look at the upward case first. Let's do upward. What would happen in that case? So in that case, let's say I'm going to choose my positive y direction to be upward because it's in the direction of the acceleration. Now, here's another thing I should point out. So always try to choose your positive direction in the direction of the acceleration. Now, the reason for that is because we have to go back and remember that Newton's second law tells me that this thing is equal to m times a, where a is a vector, which means I have to remember that if a is in the opposite direction as my positive y direction, it has to be negative. But if I always choose it in the direction of positive y, then in that case, I'll never have to worry about forgetting that negative sign, so I just don't have to worry about it. Okay. So, but if I don't, again, if my positive y is this way, but I choose a is this way, there's a negative sign between the two, which means I'm going to be off by an overall negative sign, which can definitely screw things up. So in this case, if my acceleration is that way, I want to choose my positive y to be in the same direction. Just make sure that I don't forget about that negative sign. So good. So let's look at this case. So in this case, I would say the sum of the forces then in the y direction are equal to, is it accelerating? The answer is yes. I'm going to give an m times a. So y? Well, in this case, again, I have the normal force upward, which is in the positive y direction. So I'm going to get a positive. I have my weight downward, which is in the opposite direction as my weight. So I get minus mg then is equal to ma. So in this case, if I look at my normal force then is going to be equal to the mass times g plus a. So what this says then is that's what? If my elevator is accelerating upward, I'm then going to increase my normal force, which means I have gained weight by an amount of m times a. What this says. Now in the downward case, so let's look at downward. So in this case, since it's downward, I'm going to choose positive y to be downward. So now I would say, well, the sum of the forces in the y direction then are equal to, again, ma, because again, it is accelerating. In this case, y. Well, again, now I have mg, but mg is in the same direction as positive y, so that's going to be positive. So I'm going to get an mg, and then I'll get minus my normal force, because my normal force is in the opposite direction as my positive y direction, is then equal to ma. Solving this, I get my normal force then is equal to m times g minus a. So in this case, my weight has decreased, or I have lost weight by an amount of ma. So again, so in this case, again, we have to be careful. Normal force is going to be dependent on if the system is accelerating or not accelerating, also on the geometrical representation of what's actually happening in the system. Good. So there's one more force that we're going to see often. Then we'll have some other ones we'll come back to in a little bit, but let's just talk about the last one for now. Number 3 is what's known as the tension. Oops, I did this well. There we go. Tension. So tension, we're going to denote by capital T with a vector sign. So this is what we call tension. So what's tension? So tension is the force in a string, cord, rope, etc. So anything like that, right? So here's my string. So in this case, my tension is the force which is in this string. Okay. Now, for the tension, we're going to make some assumptions. So let's talk about our assumptions. Assumption number 1. For now, our strings will be massless. And this is mostly just to simplify as much as possible. Great. Other things. Number 2, string doesn't stretch. Well, let's do it this way. String has uniform mass density. So even though it's massless, we're basically going to assume that everywhere along this string that it has exactly the same mass per length, which means that it won't stretch and it won't change mass density, which means I don't have an overdensity in one place and I don't have an underdensity in the other place, which basically means that anywhere along the string then, the tension throughout the string will be exactly the same, right? Now, the other thing that it actually tells me then is that the direction of the tension force then will be along the direction of the string, right? So in this case, if my string is like this, that means my tension will be anywhere along or pointing along anywhere along the string itself. Okay, so not off in some sort of different direction, but always along the direction of the string. And the last assumption we're going to use for now, which we'll break later, is that when it comes to pulleys, will be massless and frictionless. I just gave you the punchline. We will break this later. But for now, we're going to use that. So what does this mean? So this means that if this was my pulley, and if I had a string rolling across it so that my string did something like this, okay, and then wraps around and then comes down through the other side, what this ultimately means then is that the tension in this portion of the string is exactly the same as the tension in this portion of the string. Because it is massless and frictionless, it's just the same, okay? Now, let's talk about the direction. So basically here, what this means then is the direction of my tension will be along the direction of the string pulling in this direction. And on this side, it'll be along the direction of the string pulling it in this direction. So it would be my 2 tension forces. Okay? Now, things to note when it comes to string. So strings are a little bit complicated in the fact that if I was looking at this situation here, right? So here I'm holding it up here, and then I have my keys down here. Now, as far as the keys are concerned here, I know my keys have a weight to them, which means they're being pulled in this direction, but they're not accelerating right now, which means they have to feel another force in the opposite direction, which is then the tension force. So as far as my keys are concerned, they have a weight in this direction, and they also have a tension force. I'll do that green. I said green. There we go. In this direction. So this is my tension. Okay. Now, as far as my fingers are concerned, my fingers are being pulled downward because of the string itself, which means that as far as my fingers are concerned up here at the top portion of the string, my tension force is down in the opposite direction. Now, does that mean anywhere else along the string, it's going to be in one direction versus the other direction? Or can I simply say that, well, this portion of the tension cancels this portion of the tension, so I don't have to worry about the tension? Well, ultimately, in that case, the answer is kind of yes, in the fact that if I'm looking at this portion here versus this portion here, I know that they're not accelerating away from each other, which means the tension here does have to be the same as the tension here. But what that also tells me then is when I'm looking at a situation like this, which has multiple objects, i.e. this portion here and this portion here, I'm not going to consider both of them simultaneously. I'm going to look at one at a time. We'll talk more about this in a little bit, but we have to talk about Newton's third law first. Fine. Basically, the point is when it comes to a string, we have to be a little bit careful in the fact that the direction of the tension will be different depending on how I'm actually looking at the string. But I simply can't say that the two are going to be canceling each other, which I know is kind of true in this case, but it's also not important, at least at this stage. Okay? So anyways, this is a tension. A tension, again, is anything that is going to be in a string, rope, cord, etc. And again, we're going to say that they are massless. The strings are themselves. They have uniform mass density, which basically means that, again, the direction of the tension will be always along the direction of the string. And then when it comes to pulleys, that pulleys will be massless and frictionless. But again, we will break this later. But again, that just means that if I had something like this with a pulley, the tensions on the two sides are exactly equal to each other. So good. So that's Newton's second law. So before we start getting into applications of Newton's second law, we still have to talk about the third law, and then we'll talk about the third law in the next video. So that'll be the topic of the